Hi, this is John Regier again, and this is going to be the second video for week 1 of CS 1030. So in this video, we're going to keep looking at the foundations of computer science, and we're going to start off by looking at 3 of the things that make computer science what it is. So the first one is representation, the second is abstraction, and the third is the idea of algorithms. And we'll talk about each of these real briefly now, and then we'll look at these all in a bit more detail as the course goes on. So what's representation mean? The idea is that computers have to store a lot of data, and they also have to access it in specific ways. So for example, if Google is storing some sort of a representation of all the web pages in the world, or all of the ones that it indexes at least, then that representation has to be specifically chosen to enable rapid searching. And if the representation chosen by Google doesn't enable rapid searching, then of course they can't do their job. Similarly, the representation that Netflix chooses in which to store movies has to facilitate streaming those movies out to lots and lots and lots of people at once. So on Friday night, we can all watch our favorite shows. Also, Facebook, for example, needs to store this gigantic graph of billions of human beings with all the connections between them and allow them to like each other's stuff and all the stuff you do on Facebook. And this is only possible if they choose the right representation for their data. So this is something that's really important. So let's look at a specific example. So here's an image that I found on the internet. And this image shows a bunch of pretty flowers. But the question is, how should the computer represent it? And in particular, how should the computer represent it by sending a stream of numbers that are all in the range 0 to 255. So if you know how we do this kind of thing, then you know that one of the easy ways to do this is to map the colors in the image into numbers in 0 to 255 or something like that, and then to just send a series of these colors, one for each pixel, and the person on the receiving end of this representation of the image can then reconstruct the image. And of course, that'll work, but it's a really bad representation and nobody uses this in practice because it's too big. So in practice, we use much more sophisticated representations that drop a lot of information that you can't really easily see, and they make the picture much smaller and allow us to send it over the internet quickly. So your web pages load quickly, for example, on your phone. So the representation that we use in practice for images are really elaborate and complex. They're very special purpose, not only to the fact that these are 2D images, but also to the human perceptual system. And so this idea of how representations are tailored to specific uses is extremely important, and it's one of the reasons that computers are able to do what they do in a fairly efficient fashion. So now let's talk about abstraction. So one of the key problems in programming computers, possibly the key problem, is that everything is complicated. It's just that there's a lot going on, and keeping some fraction of what's going on in your mind as you try to solve a problem can be really, really hard. And so one of the absolutely fundamental techniques that we've come up with to fight complexity is abstraction. And abstraction basically just means dropping details that don't matter and keeping details that do matter for solving some particular problem. And this explains, for example, why there's so many different programming languages. So some programming languages make it easy to do certain things and harder to do other things. And so, of course, that's why we use them to do certain problems. And so just as an example, the most popular programming language on Earth is, as far as I've heard at least, Microsoft Excel, which is to say that more people write programs in the Microsoft Excel spreadsheet than write programs in any other programming language. And at first you might think that the spreadsheet, well, that's just a spreadsheet, it's just tables of numbers. That's not really a programming language. But hiding behind the spreadsheet, there is a real programming language that allows you to do really sophisticated things. So what is an algorithm, though? So an algorithm is a mechanical procedure for solving a specific problem. And so if we have something that we need to do, like finding a particular prime number, or sorting a list of people, or finding finding the people in Facebook that you're connected to, this always requires an algorithm. And the kind of key thing here is the steps in the algorithm have to be so simple that the computer can do them. And they also have to be expressible by a person like you or me. And this is just fundamentally, not such an easy thing. And this is what we're gonna have you spend basically most of the next 4 years learning how to do, is come up with algorithms to solve problems. And so we're not gonna be able to completely solve this problem this semester even, and certainly not today, but we can at least get started at what's going on here. So one interesting thing is that almost any problem can be solved using a wide variety of different algorithms. And then it turns out that some of the algorithms are better for some purposes and some are worse. So for example, if you wanted to sort all the people in the University of Utah by last name, there might be one algorithm that does this the fastest, and there might be another one that does it the fastest if you only have a certain limited amount of memory or some other constraint like that. So we tend to have a wide variety of algorithms. And again, you're going to be spending quite a bit of time over the next 4 years learning these things, which means that basically when you come up to a problem in a real world, you're going to know what sort of algorithm is most likely to be a useful method of attack on that problem. So let's look at just a very few specific examples. So here on the left side of the slide, I've shown part of an algorithm for solving a Rubik's Cube. And the reason I use this example is because what I want to show you is that an algorithm doesn't have to be a computer program. It really is just a series of mechanical steps. As long as we can precisely describe to another person or to a computer how to solve a Rubik's Cube, then we have an algorithm. On the right-hand part of this slide, you can see that we have a picture or part of some instructions for assembling an IKEA piece of IKEA furniture. And again, it's an algorithm because it gives you a precise series of steps which you can use to solve a problem. Now, the IKEA algorithm is not one that we could use, that we could get a computer to use, but it is one that we can implement as a person. So here I'll give one more example. So in the New York Times Magazine every Sunday, this thing called a spelling bee comes out, and it's this collection of letters. And what you need to do with these letters is find the most English language words that you can, each containing 5 or more letters, and all of which contain the letter in the center. So it has to contain L here. So one thing we might try to do is design an algorithm to find all of the words that solve this. And a couple of years ago, my older son, who's in high school at West, was taking a programming class, and he was writing some Java code to solve this, and he successfully did this, but it was a lot of code. It was like hundreds and hundreds of lines of code, because Java isn't necessarily the best possible language for expressing this kind of algorithm in. So I sat down and I said that seemed too complicated. And so here's the algorithm I came up with. So the algorithm I came up with uses this special command that you find on Unix machines or on Macs called grep. And it passes a special command to the grep program. And you can see it's got a bunch of sort of random looking characters in it. But in the characters, you can see here that, for example, we have the letters from the spelling bee. So we're saying we need to find those. We need to find at least 5 of them. And then we're going to look for arrangements of those letters in a system dictionary, which is on my Mac that I'm using to prepare the lectures here in the file user share dict words. And then finally, I wasn't able to express the constraint in the first call to grep that we have to have L in it. It turns out that that's hard to mix that constraint with the other constraints on the spelling bee. So we separately filter out words that could contain L in a separate grep command at the end. And so you might or might not like this program. You might not think this is readable. You probably don't, because you most likely haven't been using this command. But you have to admit that it is at least a whole lot shorter than maybe 500 lines of Java. So the point of this is that we use algorithms to solve problems. Algorithms contain a collection of discrete steps to solve a problem. And we express algorithms in a variety of ways, in a variety of programming languages. And some of those might be really good choices, and some of those might be really bad choices. So for example, later this semester, we'll look at a language called assembly language, which is programming in the actual low-level instructions that the computer understands. And if you wanted to solve a spelling bee using assembly language, it would be way worse than Java. It'd be thousands and thousands of instructions you'd have to write, and it'd be very, very hard to do and hard to debug. So that would be a bad choice. Java was sort of a medium bad choice, maybe not horrible, but not great. And then something like grep is actually really good, as long as you can sort of get over the fact that it's kind of ugly here. So what's a computer? A computer is a device that takes input, executes an algorithm on it, and produces output. It may terminate after doing that once. It may do that same thing repeatedly, but that's fundamentally what computers are and what they do. And what we do with this, what we do with algorithms, is to solve problems in the real world. So one thing you might be asking is, why are we studying computer science? Why do we care? Well, from your point of view, a really pretty good reason to be here is that it's pretty easy to get a decently paying job if you know how to program computers. It's just something that society right now happens to value. So that's a good reason to be here. Another reason is that computers have fundamentally changed society and are continuing to do so. And we can understand the process better if we can understand what's actually going on inside the computers. Another reason is that programming really focuses our thoughts, really focuses our effort, because we have to come up with this unambiguous collection of instructions for the computer if we want to design algorithms. And doing this is sort of fun, kind of a challenge that forces us to build rigorous disciplined thinking habits. And so this was going to cause you some amount of frustration this semester and in other semesters while you're here, because it's pretty hard to force our brains to do these things. That's sort of not, in some sense, a really easy or natural thing. But that's why we're here. We're here to get you started on the path of learning how to do these things. And finally, computers are fun, of course. We can use them to solve math problems. We can use them to make games. We can use them to make interesting virtual reality worlds. We can do all sorts of things with them. And so this is really some of the reasons why we should be studying things and why we should be learning this topic. Thank you.